Hi, I'm Jason Huffman with Huffman Welding and Machine. Like to take you around our shop today and show you some of the STEM and engineering related jobs that we do here at our shop. We are a job shop that specializes in building production equipment, very specialized machining projects or fabrication projects. We have CNC or computer numerically controlled equipment. We'll show you some of that today. We have computer controlled press brakes, which bend metal, machining centers, horizontal machining centers and vertical machining centers, and lathes, which are all machines that cut metal with cutting tools. Robotic arm plasma cutting systems that will show you that process all forms of structural material, square tube, I-beams, channels, and there's an actual robotic arm. They call it the Python arm, as in the Python snake. It can cut all sides of material as it comes through. All of these items have to be programmed and designed in our engineering department, and then it's sent out to the shop, and our skilled operators have to set up the machines, program, make sure the program's correct, and run the program. The guys often write their own programs, so we're very heavily technology and engineering based throughout our whole process. A lot of math, and all the applications that we use. But yeah, we'll kind of take you through all that equipment. You can see on our walls, these are just some of the examples of the stuff we build. Some of it has piping, lots of welding, lots of machine components. We have a lot of precision assembly. We have high-skilled expert assembly teams that put together equipment, make sure the fit, tolerances, and all that go together well. And that kind of wraps up our shop processes when we're building a pretty piece of equipment. We have to machine the parts, weld the parts, form, bend some of the parts, paint them, and then we have to get it all put together so that it works correctly. Whether it's spinning at a high RPM or it's whatever it's doing for our end customer, we're building the machinery that they use in their factory. Let's put together a fun little simulation. This is just kind of a neat thing. Catapult. This is all modeled in 3D Inventor. Every single little piece of that, he's got a design, and then the program can simulate what it's actually going to do in the field. And this is our 3D printer. We've used it for prototype work, as well as some parts that our customers actually need and use in their production. It's nice for quick prototypes or for parts that may need just to get printed quickly versus an expensive machine part. And here's another design that Steve's working on today. It's a full 3D structural model for a project we're working on. This is a parametric modeling. It's a different type of modeling than our Inventor 3D modeling. All those members that we cut in our Python X will be exported from this program directly into our machine and ran. For the expertise, math, and trades knowledge that you have to know to be able to do this type of work, DJ is rebuilding a piece of equipment that is probably 20 years old. He has to go through and he has to understand precision measurement, fits, tolerancing, and overall mechanical assembly to be able to troubleshoot what's wrong with a piece of equipment, figure out how to go about fixing it, then make new parts or repair the old parts to get it put back together correctly. So this is our 6,000 watt Bystronic laser. It's a CO2 laser that uses compressed air or compressed nitrogen to cut out material. It's similar to, some people know what a plasma cutter is or oxy-fuel cutter. It's similar to that. It's much higher speed. We have a dual change-out table, so it can almost always be running. You can be unloading and loading material and unloading parts while it's cutting, so you can run. There's a computer screen that controls all the ins and outs of what you're cutting. Jared's operating it today, and he's got to make sure that the machine's set up correctly with the right parameters, for the right material, that the parts are programmed correctly, and make sure that the machine's running. This is our 250-ton AccuPress. It's a precision CNC press brake. It's 12 foot long on the bed. The tooling that is in there is the highest precision grade
tooling that they make today. It's called the new standard Willa tooling. That we have parts that get designed, and Josh programs it on the computer and tells it, you know, the bend angles, the thickness, you know, basically draws out the part, picks out, make sure that we have the correct tooling in the machine, and then the machine will bend it up for them. We have special arms on this machine, which is kind of unique and cool. On big heavy parts or really large, hard to hold sheet metal parts, those arms will actually move up and down with the machine so that the operator is not holding a big piece of heavy material or a flimsy piece of sheet metal. Those arms will actually lift it and bring it back down for you for it's just an ease of use option. But you can see what Josh is doing here. There's a lot of technology that goes into running this machine. We have a manual press brake right over there. It's a more of a traditional press brake where you put in the tooling, but then you hit the pedal and it comes down and bends it, and it's all a manual process to adjust the bends and do the different types of bends. Here, he does the majority of the setup on the machine itself.
The accuracy of this machine is pretty astronomical. You can repeat any degree that you want repetitively, time after time after time. Anytime that I want to come back to this program for its definite name, I can come to this. Automatically gives me my profiles. If I hit the start sequence on it, it automatically knows what's going on and gives me everything that was already programmed in there. We can go back and simulate all of the different bends that are on this. That's on one profile. On the first profile, same situation. I can simulate that. As you see, it's completely different. And it remembers everything that was in there and every altercation we made to the program, so you can go back to it anytime that you want to. And that piece came out within 0.15 of a degree, which is close enough for just about anything.
Here is operating the machine right now. He has a large computer screen here where he's got to make sure that it's pulled up with the right program. The material automatically in-feeds and cuts it 100% complete and injects the material on the out-feed conveyor. This is the inside of the machine. So there's digital cameras showing what's happening right on the screen. This is a auger repair that we're doing. The end of this was wore down. We had to turn it down. Ryan is building it back up with weld, and then we'll remachine it. This is a semi-automated weld positioner. The positioner at the end is actually turning the piece. Ryan's got a fixture set up to where we're able to weld that up in a semi-automated way, so you're not having to manually do it. These are our two Doosan CNCs that Rick's operating today. He has a computer over there where he can not only design the parts, but he has to program them, set them up fully to machine the final part. This is a lathe, and it's got a live milling option right on it, so you can both turn and mill on the same machine. And it's got a bar feeder, so the material can be in-fed automatically. This is a mill, a vertical mill with what's called a fourth axis to rotate parts. So we can turn a part like this complete on this lathe with the engraving complete. We machine that engraving in it, do different parts like this. There's a large custom pin. We machine this with the threads, the engraving, the hex. And that's all done automatically in this machine and spit out complete. So right here, the part has been modeled, and right now the CAM software is automating the cutting process so that you can check it to make sure it's going to do what you want it to do. Then if you look into the machine itself now is automatically going through and cutting that after Rick's got everything programmed and set up. So this is mid-process, and there's still some machining left to do on it.
Okay, so what I'm doing here It's machining this bore out to fit these bearings. So these bearings are going to have a 4,000 press fit. So this diameter here, I measure and do my math and figure out how much I need to shrink fit that into there. And after that's shrunk into there, then this pin will slide through both of those bushings, and then a bucket pivots on this. So this pin is the pivot point, okay? So in this job, you need to know trigonometry, geometry, basic math. All these skills are good for this job.
So for your activity at home, I was hoping that you might have some toys that are similar to what I have out in front of us. So for your activity, I want you to grab one of your toys at home. Everything we do revolves around movement and power. You know, your toys move just like a real excavator would. Look at the way it spins on an axis, the way it pivots on a pivot point. In our shop today, we were fixing a pivot point, making sure that it functioned correctly. You have hydraulic components that move arms up and down in real life, but all of these pivot points have to spin, go up and down. On this pivot, these arms have to support it, this arm, these pivots, and you got another cylinder and another dual pivot to make this excavator function. It's the same thing in all the equipment we build. Everything moves either in a linear fashion or through pivots and joints. Same thing with tractors and the way the buckets move on that. When you're playing with your toys, take a look and see if you can figure out what all has to move to get the end bucket to function the way you want it to. Take time to look at all those joints and what it takes to get the end result that you're trying to achieve. Thanks.